So a solution to a system of equations is the point of intersection. That's what it looks like on a graph. But what else can you say about it? It's the point that does what to your equations? Makes them all true, right? So it's the point of intersection. It's the ordered pair that makes all your equations true. And we've looked at these with lines, but now we're going to look at these with the quadratic equations that we've been looking at, with all these conic sections that we've been looking at. My question is, how many possible solutions could you have when we're talking about conic sections? And with the conic sections, we could be looking at a parabola and a parabola, or a parabola and an ellipse, or a circle and a hyperbola. There are lots of different configurations. Is it possible to get 0 solutions? Yeah. Can't you think of 2 conic sections that would never intersect? A hyperbola that goes up and down with what other conic section?
A circle.
A circle, but where would the, yeah, I mean, and there are lots of ways that you could configure this, right? Here's the hyperbola. If there was a circle right here, they would never intersect. If there was a circle right over here, they would never intersect. There's lots of ways to do that, isn't there? Okay. You might even be able to, I mean, an ellipse would work the same way, wouldn't it? Maybe a parabola, depending on how that parabola is. Maybe a parabola that kind of went like that would never intersect that hyperbola. So I think we can get 0 possible intersections. Could they intersect just once? Yeah, how? What? Okay, the vertex of what? A hyperbola and a parabola. Okay, so if I use this hyperbola, if I use this vertex, how would my parabola have to open to give me 1 point? Up. If it opened down, how many points of intersection would I get? 3. So it looks like I can get up to 3 as well. Could I get 2 possible points of intersection? How? Okay, maybe here, and it's my parabola is opening down, or a circle and what? Maybe a circle and an ellipse, right? Depending on how it's set up. If your circle, this is your circle, and if your ellipse is inscribed and it just intersects there and there, right? So I could get 2 points of intersection. I could get 3. Could I get 4? How could you get 4? Okay, yeah, if the ellipse extended outside, there's one possible configuration. Okay, there are lots, though. Could I get 5? Is there any way to make any of these conic sections intersect 5 times? Yeah, that would only be 4, right? Is there any way to get 5? Mm-hmm. Which conic section are you talking about? An ellipse. Okay, and have the edge of the ellipse where?
The middle of the circle.
Do you want to draw? Do you want to draw it?
Not really.
Does it give you 5 intersection points? Well, then we need to see it. Because I'm curious as to what you're trying to tell me. Okay, so which 2 are intersect? You can only have 2 that are intersecting 5 times. So in that picture, maybe, but if you drew with any, I just need 2 of them that would intersect 5 times. Can you get any 2 that intersect 5 times? No. I think that your answers, therefore, are going to be anywhere from 0 to 4 possible solutions. Okay? Yes? Well, of course, then that's like what we did before with the lines, and that would be essentially the same circle. So there would be an infinite number of points, and they would be all the points that satisfy that one equation. Okay? All right. So methods for solving. We had 3 methods for solving before. Do you remember what they were? Graphing was 1. Substitution was another one. And elimination was the third one. Substitution and elimination. I'm going to tell you for what we're going to do, We're not going to worry about the graphing. Some of these won't be the nicest to graph, and even when you do graph them, they intersect sometimes at points that aren't very nice, so it's hard to see their ordered pairs. So we're going to work with substitution and elimination. If possible, I would recommend using elimination. If you can't use elimination, then you're going to move to substitution. That would be the order that I would go in. Now you're going to be able to tell probably pretty easily whether or not you can use the substitution. So let's look at this one, or the elimination. If you look at this one, the first one is the graph of what? Hyperbola. The second one, not a conic necessarily, a line, okay? So my question is, can we use the elimination method? No, why not? Trey? Go ahead, Zach. Yeah. Yeah, I mean, you could, but it's not going to help you, right? So to do elimination, since the exponents on the variables aren't the same, elimination isn't going to work real well. So let's use substitution. Which equation do you want to solve and for which variable? The bottom one for x. So x equals 3 minus 6y, right? So now that's going to go in place of x in the first one. 3 minus 6y, the quantity squared, minus 9y squared is equal to 9. Now it's just algebra, lots of algebra. You have to FOIL this thing out. 9, that'll be minus 18y minus another 18y, so minus 36y, plus 36y squared, minus 9y squared is equal to 9. And let's see, yeah, the 9s are going to cancel out, and 36y squared minus 9y squared is going to be 27y squared minus 36y is going to equal 0. Does that factor? It sure does. We can pull out a 9 and a y. So we get 3y minus 4 is equal to 0. Therefore, y could equal 0 or 4 over 3. Now, I would suggest that you write out two separate stages at this point because you need to find the x-coordinate that goes with each of these. And to do that, just go back to that's the easiest, because if y is 0, then x must be 3. So there's one ordered pair, 3 comma 0. There's one point of intersection. And the other one is if y is 4/3, x is it negative 5? 3, 2, 8. Okay, yeah, negative 5. So your other ordered pair is negative 5 comma 4/3. Okay? You see how that works? We learned these, we just didn't do them with quadratics. Okay? All right, let's look at this example. X squared plus y squared equals 7, and 4x squared plus 3y squared equals 24. Would elimination work? Yeah, I think it would work relatively well because they're both, in both cases, x squareds and y squareds. Decide which one you want to eliminate first. Okay, the y squared, that's fine. So you're going to multiply the top equation through by, or I'm going to pick a negative 3. So negative 3x squared minus 3y squared equals negative 21. So we would end up with x squared is equal to 3. Therefore, x is plus or minus root 3. Now, if x is positive root 3, put it up in here. And if x is positive root 3, then you're going to end up with 3 plus y squared is equal to 7. So y squared is 4, and y is plus or minus 2. So my ordered pair is root 3 comma plus or minus 2. Right? That's really 2 points, isn't it? Root 3 comma 2 and root 3 comma negative 2. Now I need to do the same thing, though, for x equals negative root 3. But if you put negative root 3 back in, what's negative root 3 squared? 3. So I'm still going to get this, aren't I? So y is still going to be plus or minus 2. So this ordered pair is negative root 3, comma, plus or minus 2. How many points of intersection does that graph have? 4. Okay? Yes. In this case, you could. In this case, they turn out to be the same. If you didn't do that, it's because that's always the case. And what I see is people getting into that habit and then getting wrong answers because of it. Okay. All right. All right. Let's see here. Let me see what one I have next. Okay, I'm not going to go through this one all the way, but what would you like to use on this one? You could use either one. If you used elimination, which variable would you have to eliminate? X, because they're both the x squareds. Okay? If you use substitution, which variable would you solve for? Y in the second one. Okay? But the reason I want to go past that one is because, oh, this is another good one. What would you use here? Elimination, getting rid of y's, right? What'd you say?
He said what was last year, and he goes, why?
Oh. Okay. Isn't it already set up? So you'd get 2x squared is equal to 36, so x squared is 18, so x is plus or minus 3 root 2. Now, look at this. If x squared is 18, if you plug that back in here, either one, plug it into the first one, 18 plus y squared equals 16. Y squared equals negative 2. You can't have that. What does that tell you about these two?
They're imagining.
No solution. They're not going to intersect if you were to graph them. Okay, you can't find ordered pairs that work. All right, I think I have just enough time. What do we have, 17?
It just went backwards. No, we have 16.
16. Okay, listen, I have 2 minutes to get you started on this. So, the square root of 12 plus 16i. We can do this. This is going to equal, don't you agree it's going to have to equal some a plus bi? Okay, I want to get rid of this square root, so what can I do to both sides? Square it. And if you square this side, if you FOIL it out, you get a squared plus 2abi plus bi squared. Do you agree with that? But what is bi squared? Or, sorry, b squared I squared. Minus b squared. So I'm going to write it like this now. A squared minus b squared plus 2abi. Now the reason I did this is because this is really just like the problems we did. What's the real part over here? 12. What's the real part over there? So here's one equation. A squared minus b squared equals 12. What's the imaginary part here? What's the imaginary part over there? Okay, so here's my other equation. 2ab has to equal 16. This one, though, can be simplified into a times b is equal to 8. Now, there are your two equations. It's exactly the same. Would you use substitution or elimination? Substitution. That's what I would use. All right. If I don't get these all handed out, you can just pick one up after the bell rings on your way out. But this is your assignment. It's a worksheet. Yep. Okay, this row, they're up here at the front. There you go. 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 Sorry. There you go. There you go. I gave you an extra. Okay. Ooh.